Let's continue to develop our properties of logarithms with exploration number 3. In this exploration, we're to use our calculator to show that the following are true, that the left side and the right side are equal in, for example, part A here. So if we take the log of 100 times 10, so what's 100 times 10? 1,000. Take log base 10 of 1,000, you'll get 3. Take log base 10 of 100, that's 2. And of course we know log base 10 of 10 is 1. So we have demonstrated that these two sides are equal. Now let's do this. We'll take 1,000 divided by 100. How many times does 100 go into 1,000? 10 times. So log base 10 of 10 is 1. The log base 10 of 1,000. The log base 10 of 100 is 2. So 1 equals 1. That's been verified. And now take 10 to the third. Log base 10 of 10 to the third. Of course, that's 3. We saw that property just a minute ago. Log base A of A to the R was just R. And now log base 10 of 10, we're going to get that. That would be 1. And 3 times 1 is 3. So we have shown that all of those are true. So that leads us to these next properties of logs. The log base A of m times n. So we had log base 10 of 100 times 10. Then that was equal to the log of 100 plus the log of 10. So that is the same as the log base A of m plus the log base A of n. So for the most part, a property like this will be handy when we have two logs in an equation and they have the same base and we want to write them as a single log. So we'll know how we can put those together. We multiply m times n here and make that our new argument. Well, we had this one also. The log base A of m over n, that was equal to the log base A of m minus the log base A of n. Likewise, we will most often use this property in this direction. We'll have two logs in an equation and we'll bring them together into a single log. And finally, we had log base A of m to the r, and that was equal to, look what happened. Our exponent came around front as a multiplier, so this is the same as r times the log base A of m. The exponent becomes a factor, and we still get the same result. So that's another property of logs that we'll use. Okay, let's use the ones we have so far. We have 7 properties now to work through these examples. And we're to use the laws of logarithms to simplify. So when we have 3 to the log base 3 of 18, what does that equal to? Well, that equals 18. Which property did we use? If you look back, that was number 3. A to the log base A of m. So that's what we have here. 2 to the log base 2 of -5. That equals -5. Again, property number 3. Now we have one where it's the log base A of A to the 20. So do you remember what that was? That would be 20 because that's our number 4, right? Log base A of A to the R was just equal to R. And now this one, log, what's the base on this log? It's e, right? So this is similar to this one. Log base e of e to the third is 3, again, using property number 4. Okay, let's look at example 2. We are to use the laws of logarithms to find the exact value without a calculator. So let's pull this together into a single log. It's subtraction, right? So we've got this. Let's write it like that. So that's going to be the log, since they have the same base 3 of m, 24, over n, 8. It's subtraction, so order matters. The first one is the numerator, the second one is the denominator. So that's the log base 3 of What's 24 over 8? 3. And what's the log base 3 of 3? That's 1, isn't it? So this is just equal to 1. Let's do it again. Okay, we have subtraction again, so it's log, same base, log base 8. They have to be the same base in order to do this. Okay, the numerator is 2, the denominator is 128, m over n. Let's simplify that and see what we have. What's that? 1 over 64. And 64 I can write as 8 squared. And then 1 over 8 squared can be written as 8 to the negative 2. That's another way to write 1 over the positive 2 is equal to 1 over 8 to the positive 2 is equal to 8 to the negative 2. So now we have log base 8 of 8 to the negative 2 is just negative 2.